Let's consider rotation about a moving axis, and we'll consider it from the point of view of a hula hoop rolling across a flat floor, mass m, spinning at omega. From the center mass, we have a speed, or the velocity of the center mass. Translational kinetic energy, 1/2 mv squared. But the v that we're talking about is not the v of the particular particles that are on the hoop, but rather the center mass. So the entire translational motion of the entire mass m. Then we have rotational motion, and it's 1/2 I omega squared. The moment of inertia of the center of mass, because that's what it's rotating about, so we're not considering it from the point of view yet of any other rotation axis. Combining these together, we have k translation plus k rotation. Now what about if we rotate this about an axis of rotation that's on the edge rather than the center of mass? So let's consider that. So there we go. It's the same omega we had before, but this time it's rotating from a pivot point right on the edge. So how does this compare with simply rotating the hoop along a flat surface, this rolling it around the edge? Let's investigate what that looks like, that comparison. Well, let's consider some more details of rolling the hula hoop. And this context is one in which there is no slipping or sliding, which we'll consider pretty soon. So we're going to put the hula hoop here. And just to let you know, the goal of this is to recognize that the motion of the hula hoop moving across the floor is equivalent to another type of motion, which will be the motion of the hula hoop rotated about a point that's in contact with the floor. So some more details here. We have some points of consideration. Velocity of the center mass is as shown. And every one of these other VCMs is just simply the fact that the entire hula hoop is moving to the right at a speed corresponding to the velocity of the center mass. But of course, it's rotating at the same time. So added to this, we're going to consider the motion of the particles of the hoop from rotation. So forget about translation now for a second, and just consider this thing sitting here and spinning around, rotating around at an angular velocity omega. So the points of consideration again. We have right here these 4 points, and that's the motion. The point in contact with the floor right now is, we say v from omega. The speed from the rotation is minus VCM. So as we observe this, just rotating around, this speed is exactly equal to the velocity of the center mass, but is pointing to the left. So I'm going to call it minus VCM. Up here, we have positive VCM. And on the two sides, we have really the same speed, but directed up over here and directed down here. So now we're going to combine these together. And let's consider the actual motion of the particles from our point of view, observing this thing. And that speed is just the combination of the two others. Actually, the vector combination. So here's the center mass. And the center mass is still doing what it was. And from the velocity of the center mass over here, we also have the speed of the center mass moving to the right. But now from rotation, we have a similar size vector moving up. So the combined effect is this v here. On the top, we have, at the very top, we have the motion of the center mass plus VCM is a result of omega, so it just doubles the speed. Over on this side, VCM plus, from rotation, we have VCM acting down as well. So there's the combined effect. And down here at the bottom, we have, as you probably can guess, Zippo, because if we consider it rotating about this point, at this point we can call this a virtual rotation axis. We have the effect of the velocity of the center mass here moving to the right, but from rotation we have it moving to the left. And intuitively, what's the relative motion at this point with respect to the surface? And hopefully you conclude that it's 0, because if not, then this hoop is sliding, scraping along the floor, and it's certainly not doing that, at least in this example, not if we're rolling it. So consider stationary point P. All right, it's stationary. Hopefully that makes sense now. From our point of view, the velocity of P is the velocity of the center mass, which all particles in the hoop are subject to, plus the velocity of rotation. But we're going to consider the velocity of P from the point of view of the center mass. So stick yourself at the center mass. We've already included the center mass motion. Right? Now, we include the velocity of P from the point of view of the center mass, and that's this. In other words, if you're at the center mass looking at P, you see P going this way. So the velocity of P with respect to the center mass is minus VCM. Recognize that the velocity of point P is 0. So as an equation, of course, this, just we subtract this from both sides, we get minus VCM. But it's pretty obvious. If you're observing it from here, P seems like it's going this way from that point of view. So since the velocity of P from the point of view of the center mass is the same as the velocity of the center mass in terms of the magnitude, it doesn't really matter from which vantage point, from P or the center mass, we're observing the rotation. If you're at the center mass, you see P moving at a speed r omega. But an observer at P, observing the center mass, sees it moving at r omega. Just the reverse roles here. So consider the hoop rotating about P now with no translation. All right, so we're not translating, which means we're completely spinning it around this point. Now the moment of inertia is the moment of inertia of the center mass plus mr squared, because we are r away from the center mass. Our parallel axis theorem gives us that, so mr squared. Kinetic energy 1/2 I omega squared gives us this kinetic energy, our combined I. And thus we have, for kinetic energy, the translation plus rotational kinetic energy that we saw previously. So when we spun it around this point. All this should be pretty sensible. Probably spent more time perhaps than it's worth on this, but hopefully conceptually you understand that if we rotate about this point here, really that's what we're doing at this moment in time, as this rolls across a flat surface. At any moment in time you can consider the conditions of this hoop. Since this point is not slipping or sliding, the entire hoop is effectively rotating about that point. Now granted, the floor is in the way, so the next moment, it continues to track along the floor. But if the floor isn't there, then the center mass is just going to rotate about this point. And the kinetic energy of just doing that, spinning around this point, is the same as rolling across the floor. Let's now do an example where we have a cylinder with a string wrapped around it, positive sense of rotation there, radius r, mass m, height h above the floor, and it's going to be moving with a speed, velocity to the center mass. When we do these rotation problems, it's almost by default we're talking about the center mass velocity. I'll still try and consistently subscript it. However, if not, just assume it's the velocity of the center mass. Makes a big difference if we consider a different rotation axis. For instance, we were considering it rotating about a point here on the edge. The considerations for what we're doing right now would be different. We just saw that we could consider this rotated about the edge, and there'd be some similarities. However, for this problem, it doesn't make sense because we want to find the speed of the center mass when it hits the floor. Let's use energy to do that. Work total is delta K. K2, down at the bottom, is UG1, up where it starts. So 1/2 mv squared plus 1/2 I omega squared equals mgh. Keep in mind that the moment of inertia, the center mass, is 1/2 mr squared, and omega is VCM over r. So putting those together so that we can spread out the moment of inertia, the rotational energy term here. We have 1/2 mv squared plus 1/2 I times omega squared, v squared over r squared, equals mgh. So masses go away, radius goes away very nicely. 1/2 v squared plus 1/4 v squared equals gh. So that's all 3/4 v squared. And thus the velocity of the center mass is the square root of 4/3 gh. Now let's just consider a dropped object. If we just drop an object from height h, we know that the speed at the end is rad 2gh, which is also square root of 6/3 gh. And notice that this 6/3, how it relates to 4/3. Well, just because of the fact that this system is rotating, obviously some of the energy is wrapped up in rotation, and so it results in a speed of 4/3 instead of 6/3. Well, because of that, now this is the translational part. All right, so you consider 4 compared to 6 is like 2 parts of translation and 1 part rotation. And in fact, that ratio, 2 to 1, is a result of the fact that this is a solid disk, a uniform cylinder, so to speak, and since it's 1/2 mr squared for the moment of inertia, only half of the energy that's in translation is wrapped up in rotation. So if instead this was a hoop with all the mass concentrated on the edge, then it would be equally shared. The velocity of the center mass you'd expect to be equal to 3/3 gh, or the square root of gh. And there would be a 1-to-1 correspondence between the translational and rotational energies. Let's once again consider that cylinder that's falling from being attached to the ceiling, rotating down to the floor. This time let's find the acceleration of the center mass and the tension in the string. So we have mg acting straight down. Of course, tension acts upward from this point right here. And we have an acceleration of the center mass. So sum of F is mg minus t, which is ma. Then we have sum of torques. The torque is the tension operating through the radius perpendicular to each other, and that's I alpha. And that's 1/2 mr squared alpha. Now, since there's no slipping, we have the acceleration of the center mass, which is really the same as the acceleration of the string coming off the edge of this disk. It's alpha r. All right? So you could also just consider it from here, looking at the center mass, it's still alpha r. That's the acceleration. So we can put that together. TR is 1/2 mRA instead of r squared alpha. R's go away, and we have ACM is 2T over M. All right. Now the tension from the first expression here is easily solved. We get M times G minus A. So acceleration being 2T over M, so it's 2 over M times T, which we just got as M times G minus A. M's go away. And we have 2G minus 2ACM. So we can take this, we add plus 2A to both sides, so we get 3A over here. And our final result, the acceleration is 2/3 G. Again, it makes sense, 2/3 G. If we didn't have the fact that it takes some effort to rotate this up, it would just be, of course, G And this moment of inertia being 1/2 mr squared causes the effective inertia of this to be half what a translational inertia would be. So instead of this acceleration being 50% of g, or 1/2 g, which it would if this was a hoop with all the mass concentrated around the edge. The effort to rotate, to accelerate this rotationally, given an angular acceleration, is kind of like half of the effort to translationally accelerate it. So it's a 2-to-1 thing again. 2 parts of force needed to translationally accelerate, 1 part needed to rotationally accelerate. Hopefully that makes sense. Finally, the tension, m times g minus 2/3 g. T is 1/3 mg. So let's consider the motion of various round bodies going down an inclined plane. They're going to race. We're going to see who wins. Well, if it was just a frictionless incline, of course, everything would be a tie. They'd all go down at the same rate. But we have to spin these up. And obviously, some of the geometries are harder to spin up than others. So conceptually, you probably could figure this out real quickly as to which one wins. But we have here a solid sphere, which is a moment of inertia 2/5 mr squared. We have a ring, which is mr squared, and the disk, which is 1/2 mr squared. It's going to be from height h. Well, let's do an energy consideration. Work total is delta K. K2 is UG1. Now let's note that for the moment of inertia, it's always some constant times the mr squared. So we're going to utilize that in our general energy calculation here and just leave C as C, recognizing again, as I just mentioned, C for the sphere is 2/5, for the ring it's 1, for the disk it's 1/2. So how does the speed at the end of the ramp, how is it affected by C, namely the factor of mr squared in the moment of inertia? So translational plus rotational energy equals the original potential energy. 1/2 mv squared plus 1/2 I, which is now c mr squared, v squared over r squared for omega squared is mgh. Nice cancellations. We have 1/2 v squared plus 1/2 c v squared equals gh. And the stuff on the left-hand side then, the 1/2 v squared, factors out of both of them. We have 1 plus c. Therefore, the velocity of the center mass for each one is square root of 2gh over 1 plus c, which shows you very explicitly that the larger c is, the smaller the velocity will be at the bottom. Of course, just because more of the energy is wrapped up in rotation if it is a geometry which has a large c. So let's go ahead and race them. The solid sphere wins, followed by the disk, the solid disk, and the loser in the race, at least, is the ring, because more energy is wrapped up in the rotation. But the energy has to be the same for all of them if they have the same mass when they get to the bottom. And so it's just basically a partitioning of the translation versus the rotational energy.